Hello everyone, Anthony here. I hope you all are doing fine. And the purpose of this very short video is to go through this PDF file that I have made available for you, and to make sure that you all have understood how to calculate the inverse Z transform by long division and power series expansion. So we begin by noticing that any Z transform can be represented as in the polynomial form as a sum of powers of Z, and that's the basic idea that actually we can get that either from a power series expansion or from long division. Let's look at this basic example here, and where we are giving a Z transform and the corresponding region of convergence. Notice that we can write the region of convergence in either form here. So most of the times you'll be given this, but I can also write it in this way to make sure that I understood that what is saying here, that if I divide A by Z, I get a smaller, the result is smaller than 1. So this result is smaller than 1. So when I order then the terms here, I have to follow what the regions of convergence is telling me, okay? So and then I start dividing and finding a number that multiplied by 1 will give me 1. It's 1, of course. And then I multiply 1 by 1 and 1 by this, and I set it up here. I subtract, so this will be 0, positive. Now I'm dividing this by 1, so the result is this term itself. And then do the same, I'll multiply by 1, put it here, multiply by this. Now I have a negative term here, a squared and z to the minus 2. Subtract again and divide again, I get this. I could have multiplied and continue. But this is enough to see the pattern that we are starting at 0. So this should be some a z to the minus 1 to the power of 0, which will give us 1, right? And then we would have this pattern repeating here. And the inverse transform that we are looking for are exactly the coefficients that are multiplying by z. But it's important that we make sure that we know where they are located. So we are starting at 0, then we go 1, 2, and so on. So this is clearly associated with the unit step starting at 0. So and the terms, the coefficients here are raised to the power of n. So it's a to the power of n, which is 0, 1, 2, and so on, u of n, as you can see here. In this next example, we now ordered, so we have a region of convergence which is non-causal, and the ordering is different. So now you go through this following the same steps, and you will realize that we have now a so I have to make some fixes in this non-causal result here, because now we see that the powers of z are positive. The positive powers of z are associated with this left side, okay? So this is z to the 0, z to the minus 1 here, and this would be z to the 1, z to the 2, and so on. So this is a sequence that is starting at negative 1, and it goes towards minus infinity. So this is a unit step that goes like this, minus u of minus n minus 1. Okay, so say to figure this out where it's going to, so minus n minus 1 must be greater than or equal to 0. So then we figure out, when you solve this, you will see that n must be then less than or equal to minus 1. So this is what we want, and this is the final result. Now this other example here is just to show you that you can actually either work from here or from here, which is a similar representation that we obtain when we multiply up and down by z. Okay, so now the form that we'd use as reference would be this one, more appropriate to see how I would order the terms. Say that this is absolute value of z is greater than absolute value of a, then this is should be the right order. And start dividing. Okay, z divided by z is 1 times z, 1 times minus a is minus a, subtract, this becomes positive, and then start dividing again. I want to, so if I divide, I want to find a number that multiply by z will give me this. All right, so a and z to the minus 1 to cancel this z out, I would get a, and then multiply this by a, so a squared z to the minus 1, and then continue, you get the result. Another example, interesting example that we have here is this one, which is a sum. Okay, and the numerator is a sum. Well, you can perform this at once if you want to, but you could see that you can divide it actually in two parts like this. It's 1 divided by 1 minus a z to the minus 1 minus z to the minus 1. Yeah. But since the exercise, let's assume that it was said that you should use long division, so you have to do it. But when you do so, you'll see that you have actually two patterns going on here. I have put different colors so that you can follow. I'm following the same procedures. Now you go through it, make sure that you use the region of convergence appropriately to establish the order, and go through this. And let's see. You have one of the problems that I believe you have to deliver is this one. So it's very similar to this example that I gave you here. Then you have an example here that you can use as a reference. Okay, there's one thing that I forgot to mention about one of these previous problems. Let me see if I can find it. It's actually this one, where when we get this sequence here, you see that we have always at multiplying here a 2 multiplying, but I don't have it here at 0. So 0, 1, 2, and so on. So what we can do is add it, this add 1, so I have 1 but I needed 2, so I add 1, I subtract 1 here. Okay, then I get the same, but this minus 1 here then will give me a delta at 0, and this the other will be like minus 1/3 to the power of n, and you see that the sign is alternating. So when the 0, 1, when it's odd, we have negative, and when it's even, it's so the next term actually it would be a negative term, and so on. Okay, now let's talk about power series. So you see that you have actually examples of functions that you can find and how to expand them in power series. So it's actually very straightforward. We have for sine and cosine, cosine that you'll find in some examples. So that's not much work about this. Just remember that actually when you have an exercise that involves one of these functions, you will have a power series expansion for each one of them. Okay, and we have some examples here for the logarithms. Actually, this is an example that you can find in the textbook. And another example here involving the sine, just go back and see the formula for the sine and go. And another example with exponential. And this was an example, an example that involves a multiplication of two polynomials. One is not so clear, but you can expand it, as you can see here, the sign using the formula, of course. It's sine of x, where x is z to the minus 1, okay? Just apply it, and then you start multiplying, and the exercise was to find g of 11, as you can see here. So here the thing is how to do it so that you don't get lost with all these terms. One way to do it is to go multiply one by one. Take the first element here and distribute it to this one. I get these three terms here. Then I go with the next one, another three terms, and so on. And after a while, I get the terms that I actually need. I mark them here in red so that you could see them. Please verify that this is the actual result. Okay, so all the terms g of 11, then is the coefficient that associate with the polynomial, the power z to the minus 11. Okay, now talking about the unilateral z transform. So the unilateral z transform is just a z transform that starts at 0 instead of minus infinity. And so remember that it can be expanded as a series, so n is 0, z to the 0, so I have x of 0, x of 1, z to the minus 1, and so on. So for example, if I want to calculate the unilateral z transform of delta of n, I know that this is a unit sample at 0, so that's okay. It's 1, as you can see, but on the other hand, if I delay it, so I delay it by one sample, I would have a sum from 0 to, actually I could just say to infinity, but I actually have this one sample at position at 1, so I still have 1. But if I advance it in time, so I put it on the at minus 1, so now for this example here, so this is 0, I put the sample now at minus 1. Okay, this is what you see here. So this delta will be 1 if the argument here n plus 1 is equal to 0. So then n must be minus 1 here. So I put the sample here, which is 1. If I calculate the unilateral z transform that actually starting from here, then it will be 0 because all the other samples to this side are 0. So interesting. So that's an example that I would like you to go through, but there's one thing here that when you calculate the unilateral z transform, something very interesting if you apply it to a whole system. This ZIR here is a zero input response. It means that when the input is actually 0, so if this is 0, so you get, this is your response that you will get. And on the other hand, if the initial conditions, which are the terms associated with this, are 0, so then you get this. This is the 0 initial condition response. So that you get this if the initial conditions are all 0. Okay, go to the textbook and you'll find more explanation about this. But there is one exercise that is part of what you have to deliver that involves this unilateral z transform, that you have three. It's problem 327, and you have three tasks here, but you're supposed to deliver A and B. But anyway, I did see here, because it's very similar, just that we will have a sum rather than a we have a summation here, and it's simpler. So what I did was I solved this one here, and then you go with the other two. And so what we have, so focusing on this one here, we have to write this in a more suitable form, which is this one, just a change of variable. I replaced m by n minus k, and then I figure out what the others would be. So if I say that m is replaced by n minus k, then I can say when m is infinity, m is let me see, I replace by n minus k. If m is minus infinity, then k, k, which is the new variable in this that I am using, will be plus infinity. Okay. On the other hand, when m is equal to n, so this is you got this. Now it's opposite. Okay, it was if m is equal to n, then k is 0. All right, then we go. That's the first change of variable. But when you set it up here already with the change of variable, so this is with the change of variable from here, and we're applying at the same time the unilateral Z transform. Okay, see this summation that was included here is the unilateral Z transform. Okay, but the next step then was performing an interchange of the order of summation, and the unilateral Z transform appears first. All right, and now we need another change of variable. We'll say that n minus k is equal to some L, and you do the same. So this is the change of variable that you will actually do for your exercises here. So yours, actually, this A and B they will start from here. You write the summation, so you don't have this summation here. Okay, you write that one, make the change of variable, find the proper new indices. Here I'm saying that n minus k is equal to some L. Then I figure out the other ones. So n will be equal to, need to replace n by something, which will be equal to L plus k, which I put here. So n will be replaced by L plus k. I need to figure out the limits. Okay, so when n is 0, L is equal to minus k. This is what you see here. And for infinity is the same. As you say, when n is infinity, L will also be infinity. So that's the task that you have to do. The rest is you can see from here, disregarding the this summation for a moment. Okay, so let's look at this. Then from here we separate it in two summations, two sums. Actually this is plus, and here I also forgot that I had a z to the minus L here. I will fix this and update the, so I have a z to the minus L here, and at the end I would have minus k plus L here. This must change as well. Okay, plus, then I multiply these two here. I'd have minus k minus L if you want. Yeah, I will update this. Okay, so that was it. 19 minutes, 20 minutes. Okay, it was a little bit longer than I was expecting. Guys, I will come back to you with more information about more details, about more tips about the next some of the exercise of chapter 5. Okay, good luck.